Okay, so whatever we were doing in the last class, is there any question from from anyone in this class right now? We talked about acceleration due to gravity, and we really started the topic of air resistance, right? So is there any question from anyone in the class right now?
No.
All right. Okay. So we'll continue. Is the idea of acceleration due to gravity clear for everyone?
Yes.
Uh, what's your name? Hassan, right? Hassan, do you have any clue about acceleration due to gravity, air resistances?
One of the things I mainly struggle with is to learn how that. So basically, I would answer no. I don't have many ideas.
About acceleration. Okay, so we did it in the last class. I'll just quickly go through it, and you can watch the recorded lecture, and so you'll probably get an idea as well, right? If you don't understand still, you can ask me. I'll just quickly go through it. We talked about some of the top things that are off topic, but I just told the class some things, so it's easier for you to understand where it comes from. Gravity is basically, now we know gravity is just a geometrical thing. It's not a force, really. Gravity is the, so what should I do? I think I'll go to this page, next page, and I'll add it here. I'll quickly revise gravity so everyone can benefit from this. Gravity is just the bending or the curvature or the behavior of space-time geometry. How does a space-time geometry behaves if I have any mass in that place, right? So what happens is if I put this mass, it produces bends and curves in the space-time geometry. And what happens is, well, this picture is also not a very complete understanding picture, but you can get an idea. So what happens is any other small mass gets pulled into this bend, into this curvature, right? Now, you might, of course, you must be thinking at this point that if that's the case, then this small mass should always fall towards this capital mass M, and it should be a chaos, right? Catastrophic disaster. But that doesn't happen, and that's because nothing is stationary. The entire universe is dynamic, and what that means is that this mass is translationally moving as well. It is obviously rotationally rotating, but there's also translation motion, and it's moving translationally linearly, and so is this mass, right? So because these things are always in motion, this mass doesn't fall completely into this bend, but in fact it starts orbiting or falls into the orbit of this capital mass M. And this idea is more of an Einstein's picture. Newtonian picture is Newton did not know what caused gravity. He said it's an exercise left for the reader in his book, and well, the reader, it took Einstein to solve that exercise, really. But Newton said that, well, I'll just give you a formula, and that will tell you how does one mass affect the other mass. And that was because of attraction, and that expression is gmm by r squared. You are not supposed to know this expression. I'll just give you some of the terms. That this F stands for the force. G is just a constant. It's a universal constant. It doesn't really tell you anything about the physics. It's just a constant, a number. So you can kind of forget it. Capital M is the mass of the source of gravity. What mass is really responsible for the gravity? So it depends now. If I'm considering this capital mass as Earth, as Sun, then the small mass is the Earth. It could be the Earth orbiting the Sun. The other perspective is that capital mass is the Earth. Then the small mass is either a satellite orbiting the Earth, man-made satellite, or it's the natural satellite, which is the moon, that could be orbiting the Earth. So it depends on what problem are you looking at, right? But generally, capital M is the mass of the source of gravity, which is the major source of gravity, right? So R in this thing is just the distance between the two masses. So is that clear for everyone?
Clear.
All right, good. Okay, so now, of course, when I see a mass, it's going to be falling towards the capital mass, the source of gravity, which is producing this gravity. And because it's going to be falling towards that, there has to be some acceleration, because there is a force of attraction. And we know that forces cause acceleration, or in roughly speaking, you can say forces produce acceleration. And we know, I'm sure that everyone is familiar with this expression that force is mass times acceleration, which just comes from the fact that force is really the sum of all the forces, is really the change in momentum per unit time. You don't need to know this thing right now, right? So just ignore this so far. The only thing that you need to know is this thing. And then I can find the expression for how much the acceleration is between this mass towards the capital mass M, right? And that can be done by simply saying that this force of gravity is producing this acceleration, which means I can equate it to this M times A, right? And this cancels out these M's, and you get A is gm by r squared. Now we just relabel this A as small g, saying that this is the acceleration due to gravity, right? Now this is that acceleration which this small mass M will experience when it's falling towards the capital mass M. And that's the acceleration due to gravity. All right, so you can see that small m was cancelled out. So it doesn't matter.
Second question.
Yeah, sure.
Where did G just come from? Didn't we eliminate M for M so that acceleration is equal to graphs on the bigger mass divided by r square?
We equated these two equations, because how can we do that? We're saying that this force of gravity is producing some acceleration, right? Or you can think, the easy way to think about it is that both of these are forces. So of course, this must be equal to this. Or the other thing is that you can say force of gravity is responsible for accelerating the small mass, which means that I can equate these two things. Was that your question? So we equate these two things and we get gmm by r square is equal to m times a, right?
Yes, then so small and m cancel each other, creating gm over r square is equal to acceleration. Now where did you write is equal to g? So was G always
that's what you mean. Yeah. I should have written it like this. We are relabeling this thing as G, right? Relabeling. Ignore my spellings if they're wrong. Relabeling it as G. We're just it's an alphabet. Who cares, right? Nobody cares what alphabet that we are using. We're just relabeling it as G so that we can say that it's acceleration due to gravity, right? Gravity G for gravity, G for this, right? So that's the only thing that we did. It doesn't matter. You can keep it as A. But of course, in your books and in your exams, you'll find this thing as G because that's the convention we now follow. And so that's why we relabel it as G. Mm-hmm. So is that clear?
Yeah.
Okay, good. All right, so that's acceleration due to gravity. And that's all that you have to really know about it. Of course, my point was, I was just saying that the small m, yes, the small mass cancels out, as you can see. Physically, what that means is that it doesn't matter. Suppose I'll take Earth system. This is the Earth, right? Let's call it E. And there's a person standing on this Earth. Now, it doesn't matter how heavy this person is. It will have some mass m. Doesn't matter what the value of small m is. 10,000, of course, a person cannot have a mass of 10,000. So 60, 40, 80, 100, doesn't matter what it is. It will always experience the same acceleration due to gravity, which is this gm by r square. M in this case will be the mass of the Earth, right? Which is this Earth. R square would be the radius of the Earth, because it's the distance from the center of the Earth to this person, right? And that's just the radius of the Earth. So once you put in the values, you get G is equal to 9.81 meters per second squared. Right. So what you're doing is you're putting this value of constant G, which is, if I remember, 6.67 into 10 raised to power minus 11. And then you put the mass of the Earth divided by the radius squared of the Earth, and you get 9.8 meters per second squared approximately. So what I'm saying is that this value of 9.8 meters per second squared is the acceleration that you will always experience if you're standing on the surface of the Earth.
What
Doesn't matter what your mass is. Sorry.
What exactly is G? Like the capital G?
The capital G, you're right. So it's just a universal constant, also known as the Newtonian constant of gravity. Universal, yeah, a universal constant of gravity, right? Or Newton's universal constant of gravity. It just comes from the fact that we say that the force is proportional. It is directly proportional to both of these masses, right? M and small m. So if the larger the mass, the more the force will be between these two masses. And it is inversely proportional to 1 over r squared. So I can write all of this, I can combine all this and say they are proportional to m divided by r squared. I've just combined all these three, right? And then because this is proportionality, if I want to equate it, if I want to say that it's equal to this thing, then you just add a constant, any constant, and then you multiply that constant with these things. So m by r squared. Now this constant comes from doing some experiments. You do an experiment and you find the value of this constant. All these experiments that we have been doing, whether they be very simple or very complicated and precise and accurate, all the experiments give you a value of 6.67 into 10 raised to power minus 11, which means that it really is a constant. And so we just give it a name as capital G, Newtonian constant of gravity. Right? And in physics, when you do physics, of course, it's not for you, but when we do physics, you can say, I would not like to use this term, but when you do high level physics, things like quantum field theories and so on, you set all these constants to 1, right? G could be set to 1. There are different constants, h bar, speed of light, all of these constants are set to 1. You don't really use this equal to sign, you just say that these are 1, so that you can just remove them from your calculations, because these constants are not telling you anything about the physics of the situation. And at the end of your calculation, because the calculations are so lengthy, you just add them back in the final result. So the constants don't matter. The proportionality between the two variables, those variables are important. So this proportionality is telling you that force will increase as any of the mass increases, or the force will decrease 4 times if radius increases 2 times, right? Because there is a square on radius, right? So is all of this clear for everyone? All right. Okay, good. So that's gravity, and that's the acceleration due to gravity. You can clearly see that the acceleration due to gravity, this thing, would be different for different planets or different masses, different stars, because of the fact that m can vary for different planets, and the smaller the planet, the smaller the strength of gravity is on the planet, where g is telling you about the strength of the gravity, right? So that's why on moon, it's easier for you to jump and stay in the air, take some time to come back down compared to on Earth, where because on the moon, this value of a G on moon is about 1.6 meters per second squared compared to this value on Earth, which is 9.8 meters per second squared. What this means is, so let's see what it means, right? What it means is that if I have the surface of the Earth, then if I jump on this surface of the Earth, I would come back to the Earth with a velocity of 9.8 meters per second. Every second that passes, my velocity will increase 9.8 meters per second every second. So that's 9.8 meters per second squared. So that's what acceleration is. So as every second that passes, my velocity would start increasing by 9.8, and 2 times 9.8, then 3 times, then 4 times, then 5 times 9.8. So every time it will keep increasing by 9.8. And on the moon, it would increase by 1.6. So that's why it's easier for you to stay above the surface of the moon for a longer time, because your velocity increases in minute amounts. So is that clear now for everyone? The idea of gravity. This is a Newtonian's picture of gravity. It is very useful. Don't get me wrong, it's very useful for most part of it, but it's a picture that we have now abandoned in the modern era. We use Einstein's picture, and Einstein picture is so far the most accurate and precise picture of gravity, right? But of course, you can do a lot with Newtonian's picture of gravity as well. So that's acceleration due to gravity. And while we're at it, we'll also talk about weight. And the concept of weight is very simple. It is the force of gravity that any mass will experience, right? So it is defined as the product of mass times this acceleration due to gravity, right? Now, because this is kilograms, this is meters per second squared, because it's an acceleration, the units for weight are newtons, or kilograms meters per second squared, right? So we see that weight is really a force. And if weight is a force, then what is weight really? It's just the force of gravity that any mass would experience, whether it's on the surface of the Earth, on the moon, or on any other planet, depending. This constant would depend. So of course, the mass is the amount of, a rough definition, roughly speaking, is the amount of stuff in an object. Of course, then you can ask what stuff, right? And then you can go into philosophy of it. It's really the energy, but we'll not go into that. There's no such thing as mass, really. It's just energy, and mass kind of comes from that. But anyways, the mass will always be a particular value if it's a constant, but the weight can vary. So on different planets, your weight will be different. Another thing that I'll like to end this topic of acceleration due to gravity with is, if you remember this expression that we wrote, right, this one, we can see that G would change if the distance between the two masses change, or the radius of the Earth or radius of any planet changes, then G will also change. So for example, if you take Earth, if you're on the equator of the Earth, the acceleration due to gravity would be different if you're compared to if you're on the poles of the Earth. Or suppose that as I increase my distances from this surface, as I go above Earth, the acceleration due to gravity keeps on decreasing, right? Because you can see that it's inversely proportional. So as I move away, the gravity, strength of gravity decreases, decreases, and decreases, right? All right, so that's gravity. And then we started the topic of air resistance. So before I go back to air resistance, everything is clear for gravity. Is it all understood? Acceleration due to
Yes, sir.
gravity. Okay. All right. Good. Okay. So air resistance. We started with air resistance, and I gave some couple of examples in the last class. For some of the students, I know we're repeating some of the things, but if it's was air resistance clear for everyone in the last class as well, or is it you all wouldn't mind me going through it over again, right? Okay, I think it's okay. All right. So air resistance is really, I'll give you an example first. Consider that you have a car that is moving on a road or something, and of course, there is some air. Air is made up of different molecules. So it's not an empty space. There is something over there still. So the car would have to fight against these molecules to move forward. So these molecules are of air, right? Air molecules. Now what the car does is when car moves in this direction, where I have made this arrow, it will try to get rid of these molecules. It will push these molecules out of its path. And I gave an example that suppose that there's a crowd of people and you have to reach your destination and you're very impatient, then you'd start pushing all these people away from you and you'd want to go to your destination. So these people over here are like air resistance. So in the same way, these molecules are producing resistance to this motion of this car. And that's what air resistance is, that the car has to fight against these air molecules to move forward. Similarly, if an object is falling or rising from the ground, then it still has to do in the same way. It has to fight against these air molecules, knock them out of its path, and then continue its path, right? So these molecules are producing some resistance to the object, and that resistance is air resistance, right? Now, you can have two different scenarios: falling without this resistance, and in that particular scenario, you call that a free fall, right? So whenever you see a word free fall, it means that you're freely falling. There is no potential that is acting against you, or no resistance that is acting against you, right? So in other words, you have seen this term used so often that we say ignore air resistance, and then air resistance, poor air resistance feels left out, right? But we ignore it and makes our life easy. Then we have something that is falling with this air resistance. Now, when you're falling with air resistance, what happens is, suppose that you have down, suppose that there was no air resistance at this point. The only force that acts on this object is anyone?
Is it gravity?
Yeah, it's gravity, right? So it's the weight of this mass, which is m multiplied by g, right? Now, that's the only force that acts on this system. You can hear me properly, right? I keep getting a pop-up of your internet connection is unstable. Am I clear for everyone? Audible?
Yes.
All right, good. Okay, so without air resistance, the only force is m times g. Suppose that there is some air resistance, then it would be acting in the opposite direction because it has to slow down this path. So the air resistance, let's just call it small f, would be acting in the upwards direction if the motion is along this direction, right? Now, you can think of it as a frictional force to this motion. And what happens at one point, let's see, there's a concept of terminal velocity. And it's an extremely simple concept, because what happens is, suppose that this friction was not there present, right? Then what happens is this mass falls and its speed increases by 9.8 meters per second every second, right? Every second, the speed will increase by 9.8 meters per second. Now, suppose that there is some air resistance, then that air resistance, depending on its value, it will slow down this increase in speed. So if it were increasing by 9.8 meters per second, maybe now it might increase by 2.2 meters per second. Because it's in the opposite direction, this friction. So when you add these two, it would be, so how do we do it? We first of all, we have to define a coordinate system, and we can say, we can say that downwards is positive and upwards is negative. Now, this thing is completely up to you. It doesn't matter. You could have said upwards is positive, downwards is negative. There's nothing special about positive and negative, right? But if you're choosing one of the directions to be positive, then the other must be negative. That's it. Now, suppose if I'm saying that downwards is positive, then I'd say plus mg, right? Because this would be positive, minus f. So you're getting rid of some of the force from this mg. So the result, suppose it's a number, this number will be smaller than mg, right? It would be smaller than mg itself, whatever the result you got from mg, right? So it's taking some part away from this force. What would happen at one point? These both forces would become equal, right? So at some point, mg is equal to the frictional force, because as you fall down, the strength of the frictional force, the more your speed is, the more the friction force is, right? So because when you're falling down, your speed is increasing by 9.8 meters per second every second, the more you fall down, the more friction you will start developing, right? So at one point, that means both these forces become equal. And when this happens, at that point, the velocity of the object is known as terminal velocity. So it reaches a particular fixed velocity, after which this velocity will increase no longer, and hence it's called as the terminal velocity of this object. So that's the idea of terminal velocity. So is that clear?
Yes, sir.
Okay, so there are some points that I'd like to point that you should have understood, that this air resistance, I'll just say AR for air resistance, opposes direction of motion. Direction of motion. So from the explanation, was this thing clear? That it will always oppose, or meaning that it will be in the opposite direction of the motion. So is that clear for everyone? I'm just summarizing air resistance right now. Okay, so that's clear for everyone. So I'll just take this thing. All right. Okay. The next point was that what else did we talk about? Yeah. So air resistance increases if speed increases. Speed of the object, obviously, right? If which is falling. Is this clear as well? Why would it increase?
Wait, sir. It just started at 9.8 meters every second and it decreased to 2.2 meters every second. But gradually, with like when the more time, the air resistance will naturally become equal to F, which will turn into terminal velocity. How can that be? Air resistance is not increasing then.
Oh, no. I'm not saying that the speed became 2.2 meters per second. You should, I can see where the confusion came from. I'm saying that the speed increases initially from as speed is still increasing, right? Every second passes, the speed without air resistance, the speed was increasing by 9.8 meters per second. Now if you add some resistance to this motion, then this increase, the important word is increase in speed every second, drops to 2.2. The speed is still increasing, but now it's increasing slowly, right? So does that answer your question?
Yes, sir.
Okay, good. All right. So then this thing is clear that air resistance will increase as the speed increases, because as the speed increases, it will tackle more air molecules that would be jumbled up there, and so it would have to fight against all those molecules, and so the air resistance will also increase. All right, so that's clear as well. Okay, so the next point is, well, I did not really talk about it, but it should be kind of clear if you understand this idea of battling against or fighting against these molecules, that air resistance will increase if density of the air is increased. So let's see. Can anyone tell me why is this the case? I'll give you a hint that think of a molecular picture of air resistance. Anyone?
Sir,
Yeah.
I think I have an idea. Sir,
Yeah.
basically, you explained that you remember the example that you gave where there is a bunch of impatient,
Exactly.
individuals,
Yeah.
and you want to get
This.
to your destination faster, so you start pushing them. Air resistance
Exactly.
you said air resistance was exactly like that. And in
Yeah.
fact, like density is basically like in increased
More
density,
people,
it means that there are more molecules in a certain area, which means that like
certain
if you
area or a
envision,
volume.
yes.
Yeah.
So
Yeah.
if there are more molecules in like a certain area, then naturally the air resistance will increase and so will density. So hence both are co-linked.
Exactly, right? So you'd have to push against more people in that particular volume of space. And so because you would have to push against more people, that means the air resistance is increasing, has increased, right? If you keep this analogy, then the air resistance has increased, right? So everybody understands that?
Yes.
Okay, how about the rest of the class? Minhal, Urwa, Norsherwan?
Yes, sir.
All right, so it's clear. Okay. All right, so that's more or less, that's the idea of air resistance. And is terminal velocity also clear?
Yes, sir.
I know some people have a tough time understanding terminal velocity, but it's that simple, right? When the forces become equal, really, you attain a constant speed and your speed will no longer increase. And that speed is known as the terminal velocity. And that's it.
Sir, let me
Yeah.
just confirm one thing. That is
Yeah.
terminal velocity is when mg and f become equal, right? So the overall movement of the object net in acceleration is 0.
The net acceleration is definitely 0. Yeah. And that's why it